The James Webb Space Telescope has rapidly become the most powerful tool ever built to study the universe. It is not merely a successor to the Hubble Space Telescope, it represents a generational leap in our ability to peer into the deepest corners of the cosmos. With its massive 6.5-meter gold-coated mirror and its suite of highly sensitive infrared instruments, Webb has opened a window into time itself, allowing us to look back billions of years and forward into new worlds that may harbor life. This telescope isn't just about observing stars and galaxies. It's about reshaping everything we know about space, time, and perhaps even life. Webb was built to answer some of the biggest questions humanity has ever asked. How did galaxies form and evolve? What lies within the atmospheres of distant exoplanets? Are we alone in this vast universe? For decades, these questions seemed like science fiction. Today, they are scientific targets, and Webb is giving us answers. In one of its most fascinating discoveries to date, the telescope was pointed at a star about 120 light-years away in the constellation Leo. What it revealed shocked scientists. Orbiting this star is an exoplanet called K218b, and for the first time ever, astronomers detected carbon-bearing molecules in its atmosphere. Compounds that, here on Earth, are deeply linked to life and organic chemistry. More intriguingly, these molecules hint that K218b may harbor a vast subsurface ocean beneath a hydrogen-rich sky. This is more than just an astronomical observation. It's a potential game-changer in the search for alien life. K218b. The ocean world candidate K218b is not a new discovery. It was first identified during NASA's K2 mission, an extension of the famous Kepler Space Observatory, which focused on finding Earth-sized exoplanets orbiting within their star's habitable zones, the region around a star where conditions might support liquid water. K218b caught scientists' attention because it orbits within its star's habitable zone. But its size and mass immediately set it apart. At about 8.6 times the mass of Earth and with a radius 2.6 times larger, it belongs to a class of planets called Sub-Neptunes, larger than Earth, but smaller than Neptune. These kinds of planets are entirely missing from our solar system, making them mysterious and fascinating. For years, astronomers speculated about what these sub-Neptunes might be like. Do they have thick atmospheres like gas giants, or rocky surfaces covered in water or ice? Are they mini-Neptunes, or super-Earths? For K218b, the puzzle remained unsolved, until the James Webb Space Telescope pointed its powerful eyes toward it. Webb's revelations. Carbon compounds detected using its near-infrared spectrograph, NIR spec. Webb analyzed the starlight passing through K218b's atmosphere as the planet transited in front of its host star. This technique, called transit spectroscopy, reveals the chemical composition of the atmosphere by identifying specific absorption patterns, like a fingerprint for each molecule. The results were stunning. Webb detected methane, CH, and carbon dioxide, CO, both carbon-based molecules essential to life as we know it. These compounds are considered potential biosignatures, especially when found in specific ratios and in the absence of other elements like ammonia, which was notably not detected. The lack of ammonia strengthens the case that K218b might not be a gas giant, but rather a water world, an ocean-covered planet enshrouded in a hydrogen-rich atmosphere. This led researchers to propose that K218b could be what's known as a Hycean planet, a theoretical class of worlds that feature deep global oceans under hydrogen atmospheres, and that may support microbial life in ways similar to early Earth. The mystery of dimethyl sulfide, DMS. Perhaps the most tantalizing aspect of the Webb data is the possible presence of dimethyl sulfide, DMS, a molecule that, on Earth, is produced exclusively by living organisms, particularly by phytoplankton in the oceans. DMS is regarded as a biosignature gas, a strong indicator of life when found in planetary atmospheres. While the detection of DMS on K218b is still tentative and requires further confirmation, it marks a monumental step in exoplanet science. For the first time, we may be on the verge of detecting a chemical uniquely associated with biological activity, on a world 120 light-years away. Researchers are cautious, however. The presence of carbon-bearing molecules doesn't necessarily mean life exists. There are abiotic processes, such as volcanic activity or photochemical reactions, that can also produce these gases. But the combination of methane, carbon dioxide, the lack of ammonia, and the potential for DMS paints a picture that's difficult to ignore. Dr. Niku Madhusudan from the University of Cambridge, a lead researcher on the project, explains that while K218b lies within the habitable zone, it might not be habitable in the way we think of Earth. The extreme pressure and temperature conditions beneath a hydrogen atmosphere could make life very different, or even unlikely, by our standards. Still, the possibility of life existing in such an alien environment, however different from Earth's, is electrifying. What's next for K218b? Webb's next objective is to use its mid-infrared instrument, MIRI, to dig even deeper into the planet's atmospheric layers. MIRI will provide more detailed information about the planet's temperature, cloud dynamics, and weather systems, and most importantly, it will help determine whether the detection of DMS is real and repeatable. If confirmed, this would be the first time a known biosignature gas has ever been observed outside our solar system, an event that would go down in history. Even without this confirmation, Webb has already revolutionized the study of exoplanets. K218b is now the best characterized sub-Neptune in the habitable zone, and it opens the door for a new generation of telescopes and missions dedicated to searching for life. Organic molecules in the early universe, but K218b isn't the only place where Webb is rewriting the story of the cosmos. In a separate and equally astonishing observation, the telescope detected complex organic molecules known as polycyclic aromatic hydrocarbons, PAHs, in a distant galaxy designated SPTO41847. These molecules, which on Earth are found in combustion byproducts like soot and petroleum, are made of dozens or even hundreds of carbon atoms arranged in ring structures. Here's what makes the discovery truly remarkable. The light from this galaxy began its journey just 1.5 billion years after the Big Bang, when the universe was a mere 10% of its current age. That means that even in this young and turbulent period, complex carbon molecules were already forming. This contradicts previous models, which assumed that such molecular complexity would take billions of years to emerge through star formation and supernova enrichment. Instead, Webb shows us that these building blocks of life were already present, and widespread, in the early universe. Even more curious, the distribution of these molecules isn't uniform. Some regions of the galaxy are rich in them, while others are nearly empty. Scientists don't yet know why, but it suggests that the chemistry of galaxies may be far more dynamic and uneven than we ever imagined. To put it into perspective, our Milky Way is around 13.6 billion years old, and yet this younger galaxy, SPTO41847, is already as massive as the Milky Way and contains comparable amounts of carbon and oxygen, essential ingredients for planet and life formation. A new chapter in cosmic exploration. Webb's unprecedented sensitivity is what makes these discoveries possible. It can detect the faintest signatures of light from across the universe and break that light into its component wavelengths, decoding chemical fingerprints and revealing the secrets of galaxies, stars, and planets. For the first time, we're not just detecting molecules in distant atmospheres or galaxies. We're mapping them, understanding their origins, and considering their role in the larger cosmic puzzle. Whether it's methane on a distant ocean world or PAHs in a baby galaxy, organic chemistry seems to be common, not rare. That leads to profound implications. If the building blocks of life are everywhere, could life itself be more widespread than we once believed? Could it emerge under a variety of conditions, not just on warm, Earth-like planets, but under hydrogen skies, in oceans under ice, or even in places we haven't yet imagined? We are only just beginning to ask these questions seriously, and thanks to Webb, we are finally getting some answers. Final thoughts. The James Webb Space Telescope has only just begun its mission, but it is already delivering data that challenges the way we think about the universe. With every new observation, it reveals a cosmos that is more complex, more alive, and more filled with possibility than we ever dreamed. At Wave's Discovery, we believe that these discoveries are not just facts and figures. They are milestones in humanity's quest to understand our place in the grand cosmic story. As scientists, storytellers, and explorers, we stand at the frontier of a new era, where the search for life beyond Earth is not just a dream, but a focused scientific endeavor. Let us know your thoughts in the comments. What do you make of the K218b discovery? Could we be closer to finding alien life, or at least alien oceans, than ever before? And what do the carbon molecules in ancient galaxies tell us about the origin of life itself? If you enjoyed this deep exploration of the universe, subscribe to Discovery at 2.0, hit the bell icon, and stay tuned for more journeys through the cosmos. The universe is vast, mysterious, and beautiful, and together, we'll continue uncovering its secrets, one discovery at a time.